Here we are given a cone which is cut by a height 4 horizontal plane, and we need to write down the triple integral for the volume of this object in 3 different coordinates: the rectangular, cylindrical, and then the spherical. So how do we handle this? Well, first you need to think about the equations for this bottom surface and the top surface. The top surface is easy. This is just z equals to 4 because it's a horizontal plane that's covering it, right? The bottom surface, however, is a little more tricky. And it really helps if you knew that the cone, the double cone that looks like this, has the equation equals to z squared equals to the x squared plus y squared. Okay, this thing gives you a double cone, and you can figure this out by doing xy trace, yz trace, and all the level curves. So, for example, if you do xz trace, that means setting y as 0, then you get z squared equals to x squared, so z is equal to plus minus x. But what's that? That's like the 45 degree, like that, right? So you get this as the xz trace, and the same thing happens for yz trace. And then for each level curves of z, for z equals to 1, 2, 3, 4, 5, this just becomes a circle of radius z, right? So the cross sections, horizontal level curves, horizontal cross sections, which are the level curves, will be circles. So because you get circles here, you end up with this 3-dimensional surface where it's called a cone, despite the fact that it's really 2 cones that's vertically meeting. But people just call this the cone. All right. Now, it would be nice if this was really what we're given, but unfortunately, it's saying that the angle between these 2 lines is 2 pi over 3, or 120 degrees. And we know that that's not true for here because it's a 45 degree angled line, so this angle would be 90 degrees in this case. So they're different. That means we first somehow have to modify this so that the cross sections become 120 degrees. So how do we do that? And that's actually the first part that you have to figure out before doing anything else. That's the harder part. All right, so let's try this. You have something like 60 degrees here, 60 degrees here. Okay. And see, there's an easy way to just get the top half of the cone, not the bottom one, because if you solve this for z, you get plus or minus square root of x squared plus y squared. So if you just take the positive one, you get the top cone, minus 1 gives you the bottom cone. So what you want to do is just first think about the double cone that's like this. Try to find out the equation for this and then solve for z, and you'll be able to just get an equation for the top cone. Okay. All right, so you have 60 degrees here, and there's 30 degrees. And the question is, what is this line equation that would give you 30 degrees from the positive x-axis? If you know how, that would be great. If you don't know, then we can just figure it out here, because let's say we take this length 1 portion of it, then because this hypotenuse is 1, this length will be cosine of 30 degrees, and this length would be sine 30 degrees just by trigonometry, right? But sine 30 degrees, sine 30 degrees is 1 over 2, and cosine 30 degrees is radical 3 over 2. And if you do rise over run to get the slope of this, the slope m would be 1/2 divided by radical 3 over 2, and then you can simplify this by multiplying 2 top and bottom, so you get 1 over radical 3 as your slope. Now, because the slope here is m equals to 1 over radical 3, This one will just be the minus slope, m equals to negative 1 over radical 3. If you don't believe me, you can actually do the math again and figure out why. But it'll be negative, okay? And then, so think about this. You have one line, which is described as, so here we're going to say this is z and that's x, okay? So it's just like this situation. So z equals to 1 over radical 3 x would be one equation, and the other equation would be z equals to negative 1 over radical 3 x. And if you square both equations, then the minus goes away and they become a single equation called z squared equals to 1/3 of x squared. And that's actually a single equation that gives you two lines, because if you solve this, you get these 1 plus 1 minus, you get both of the lines. And what this is telling us is that whatever the equation for this, its xz trace must be this one. Now you can do the same thing for the y, and you get that for the y it should be this one, right? In the same way. And so once you look at this and compare it with the cone that you know, you kind of believe that that's true, because it's like taking this one, and because you're dividing by something, it's kind of flattened, so it's wider. So that's now you believe that this is indeed the equation for the bottom circle. Okay, so you could say this is like z squared equals to 1/3 x squared plus y squared, and then you take the square root, which is 1 over square root of 3 square root of x squared plus y squared, and it's actually plus or minus, but we take the plus one because you need the top cone. Alright, so after this hard work, here's what we found out. We found out that the equation here is z equals to 1 over radical 3 times square root of x squared plus y squared, whereas the top one is z equals to 4. And this is great because now you can write down the equation for the volume. Volume is a triple integral of 1 dv, because if you add up all the small bits of volume, you recover the volume over this three-dimensional object. And because I'm trying to go from this surface to that surface, you're going up, right? So we need to put, for the rectangular, we need to put dz first. So it's going to be 1 dz, and then let's put dy dx. This is the order that I like the best. So it's dz dy dx, where the bottom one is z equals to 1 over square root of 3 square root of x squared plus y squared. And you don't need this, so you just put this one here, okay? And then over here, z is equal to 4, so you put 4 there. And then now if you integrate in the z direction, what happens is that it's like taking something and flattening the entire thing down like a pancake. Just flatten everything like a pancake. And on the xy plane, what you get is, here on the xy plane, if you think about it, if everything is brought down to the xy plane, or think about the shadow, okay? The shadow on the xy plane would be the circle. Of what radius? Well, we don't know. So let's think about what's the actual radius of this circle by setting these two together. So if you set two things equal to each other, then you get the intersection between the top plane and this cone, and you will get the equation for this circle that you want. So you set them equal to each other. So you set 4 equals to 1 over radical 3 square root of x squared plus y squared, multiplied by radical 3, so that's 4 radical 3 equals to square root of x squared plus y squared, and then square both sides to get the equation that x squared plus y squared is equal to 4 radical 3 squared. And 4 squared is 16, and then radical 3 squared is 3, so that's equal to 48. But this is, what is this? This is a circle of radius 4 radical 3. So it's a circle of radius 4 radical 3. And you're trying to paint the entire circle using dy dx. So how do you do this? Well, that means to paint this upwards, you have to figure out this curve in the bottom and the curve on the top. So you solve this equation for y. So y squared is equal to 48 minus x squared. Take the square roots, plus or minus square root of 48 minus x squared, and we know that the minus one will be the bottom half circle and the positive one will be the top circle. And you have to also know that you do surface to surface, curve to curve, and point to point. So this is a surface that's covering the bottom. 4 is also the surface for the top. And then the curve to curve is this curve to that curve, which is the minus square root of 48 minus y squared to positive 48 minus y squared. And then once you've integrated that, then you end up like flattening this onto the x-axis, and the x-axis varies from negative 4 radical 3 to 4 radical 3, so it's negative 4 radical 3 to positive 4 radical 3. Okay, so after some hard work, we figured out that this is the rectangular case. Now, how do you do this in polar? Well, for the polar, you have to know that the z is the same z. You just have to make sure that x and y are changed into the r and theta, right? And another thing that you have to know, well, let's write down what we know about the cylindrical. Cylindrical coordinate system uses first the volume is same thing as r dz dr d theta. Don't forget this r, it's very important. You need to put that r there. And then r is equal to square root of x squared plus y squared. And then theta is equal to tangent inverse of y over x plus some alpha. Well, I talked about this alpha several times, so I'm not going to elaborate. Often this formula is not that used much. Well, I guess here it may be used, but usually this is not that important. The other important ones are x equals to r cosine theta and y equals to r sine theta. These are the things that you have to know in order to convert the rectangular into polar. And because we have from negative 4 radical 3 to positive 4 radical 3 and negative square root of 48 minus x squared to positive 48 minus x squared. I just remembered this is x, okay? And then you go from 1 over square root of 3 square root of x squared plus y squared to 4, and then you do dz dy dx. This now has to change to r dz dr d theta. And the bounds don't really change because z is the same thing, except you're not allowed to have x and y, so you have to look and say, oh, r is square root of x squared plus y squared, so this can be replaced by r. So you put 1 over radical 3r, and then z goes up till 4, so that's good. And then for r and theta, now you have to integrate this over this circle of radius 4 radical 3, right? But what does that mean? That means if you try to paint this in polar coordinates with r and theta, you have to use radial direction to paint this, right? And you can see that for any of the ray, you start painting at r equal to 0, and you end when you're 4 radical 3 away from the origin, because then you will be on the circle. So it's 4 radical 3 here. And then finally your theta goes all the way around 360 degrees, so it's from 0 to 2 pi. So that's how you do the cylindrical. This is cylindrical. And now finally for the spherical. For spherical you have to know the following formula, that spherical uses rho, phi, and theta. Theta is same as theta, so if you are trying to go from rectangular to spherical, it's often better to go through the cylindrical first, because cylindrical and spherical, they have the common theta. Rho is the distance from the origin, so it's square root of x squared plus y squared plus z squared. And phi is the angle from the North Pole. So if you had some point on 3D space, and then phi would be the angle from the North Pole. So you can draw this perpendicular line to the z, and if you view it from the side, it's like this. You have this right triangle whose height is z, and the distance from the z-axis, that's what r means. R is really the distance from the point to the z-axis. So this is r. But rho is distance from the origin, so this will be rho. And your phi is this angle. And because of that, you have some really important formulas, which is you have r as rho sine phi, and z as rho cosine phi. And moreover, just like how we had this dv for this r that had to be multiplied to integrate in cylindrical coordinates, there's also another formula for dv in spherical, which is rho squared sine phi. D rho d phi d theta. Okay, that's what we need. All right. So now we have to somehow come up with an equation for. So here the equation for the cone is z equals to. Let me write it like this. So for this cone, this is now z equals to 1 over radical 3r, right? And the question is now, what is this in terms of spherical coordinates? Because for spherical coordinates now, because you have d rho, you have to put d rho inside, and then you need some equation for the surfaces, right? So in order to change this equation into the spherical coordinate system, we have to bring it down here and replace z as rho cosine phi equals to 1 over radical 3 rho sine phi, because r is that. And you can divide by rho both sides, and then multiply by radical 3 on this side and divide by cosine phi. You get radical 3 equals to sine phi over cosine phi. But what is this? This is tangent theta, right? Tangent phi, right? So phi is now tangent inverse of radical 3, and this is actually pi over 3. It's 60 degrees. Okay. So what that means is that this equation in the bottom is now just phi equals to 60 degrees, or pi over 3. You might want to stop for a moment and think about why this would give you the cone. In fact, if you think about any point on this cone, that point will be 60 degrees away from the North Pole, right? Yeah, from the z-axis. So indeed, if you collect all the points that have phi equal to pi over 3, you're going to get this cone. And that's why you get this equation, phi equals to pi over 3 as the equation. And then, although z equals to 4 was okay in cylindrical, because cylindrical has z as one of the variables, this now also has to be changed into spherical, and z is rho cosine phi. So that means you get rho equals to 4 over cosine phi. Okay, so now we're ready to write down the equation, the triple integral for the volume. It's rho squared sine phi, that's always needed. And then you put d rho, d phi, d theta. And having d rho means you're trying to paint this region in the radial direction where the beginning point is in the origin. Okay, so it's going like that, and you see that you always start at 0 for rho because you start at the origin, but you stop the moment when you hit this top plane, which is z equals to 4, or rho equals to 4 over cosine phi. So that's why you need to put rho over cosine phi. And then once you're done with that, phi, the angles is, there are some points that's right on the z-axis, so those will start with phi equal to 0, but the maximum you can go is phi equals to pi over 3. And then for theta, that's the angle going in this direction, right? So you see that this is 360 degrees, so theta goes from 0 to 2 pi. So this will be the answer for the spherical case.